Hi, everyone.
So yeah, I'm going to talk about the work Learning-Augmented metric distortion via PQ Veto. This is a joint work with Berger, who's right here, Michal, Feldman, and my advisor, Vasilis, Gkatzelis. Okay, so for whoever is at the award session, bear with me for a few minutes because I wanted to make the model more concrete. So this work is also following the same line as the work that we discussed in the award session that focuses on the tension between classic analysis of algorithms and machine learning heuristics. So like we said before, worst case analysis is our best friend because it gives us the guarantee no matter what happened, but they could be overly pessimistic and uninformative sometimes. But on the other hand, these machine learning heuristics works very well in practice, but they're not robust. And sometimes these things that hurts us. So what we're looking for is designing algorithms with the help of some unreliable machine learned advice, such that we can utilize this advice when the quality is good, but still get the robustness that we hope for from the worst case analysis. So just to make my point more concrete, the ideal algorithm that we're looking for, again, is achieving optimal performance when the predictions are accurate without sacrificing the worst case guarantee when they're arbitrarily bad. And we have to do it without knowing the quality of the prediction. These two notions in the literature are called the consistency and the robustness, which I'm going to repeat again. So it's okay if we don't get it now. And then the framework is originally considered by Makhdiem, Nazazadeh, and Saberi back in EC'07, and later was developed to the current form by Lukoritsa and Masloratsky in their 18 paper, and then there's a bunch of follow-up work. And then, like I said before, the central question we ask is, can we get good robustness and consistency trade-off? And in addition, we want some smooth degradation from consistency to robustness. So suppose that your prediction is just slightly off of whatever you're predicting. You don't want your performance guarantee to go immediately back to robustness. You still want some good guarantees, even if it's not optimal in some sense. Okay, so let me go through a very simple example to quickly demonstrate how is it possible that we can get two seemingly very contradicting objectives at the same time. Let's consider a very simple problem that we all are familiar with, the binary search. So suppose that you have a sorted array and trying to find a number in the sorted array. We know that the best thing that we can do in the worst case sense is to do binary search, right? We start in the middle. 16 is bigger than 10, which is the number that I'm trying to find. So I go to the left. 7 is smaller. I go to the right, so on and so forth. I get 10. The runtime is log n. And we know that this is the best you can hope for. No algorithm can achieve a better than log n worst case approximation. Okay, done deal. Like worst case, it's tight. What about some practical binary search? Suppose that, suppose I tell you that all of the numbers in the array are positive, and you know the number you're looking for is 10. So maybe somehow it should be somewhere on the left instead of on the right because it's not that big. So somehow suppose that you're provided with some extra information about the location of the things that you're looking for. Well, first, one thing we could do is we could just go try it. It's constant time, right? Worst thing worse, even if this is wrong, I can just go back and run the binary search. In which case, the mechanism that I just described actually gives you one consistency and log n robustness, because if my prediction were to be correct, I got it like instantly. Even if I was wrong, like in the worst case sense, my runtime is still log n. But this is not smooth as we see, because if my prediction is one off, then all of a sudden I get log n again. So instead, what we can do is, suppose that you're provided with a wrong prediction, you go probe it and it was wrong. Instead of going back and running the binary search, what you can do is you can gradually search around it. So like, for example, in this case, if my predicted number is 20, instead of going back to running binary search, I can just go 2 steps to the left because I know 10 is less than 20, so I'm going left. So 17 is still bigger than 10, 4 steps to the left from 20. And then 8 steps to the left until I find a number that is less than 10, in which case I can just go back and run binary search. The algorithm that I just described has a runtime of 2 log eta, where eta is the error of the prediction. The prediction is just the distance between the predicted position and the actual position you're trying to find. The key point here is that the worst possible error in this particular example is n, in which case, even if your prediction is as bad as it gets, the runtime is still theta of log n. But if your prediction is correct or almost correct, your performance is going to be so much better. So this is kind of like an example of demonstrating why sometimes worst case might help us or preventing us from discovering some sort of practical algorithms. Okay, hope this makes sense. So this kind of idea has already been applied in multiple different settings. You can see like a different data structure, online runtime, approximation, algorithm game theory, differential privacy, so on and so forth. For the past 6 years, there's been more than 200 papers published in this line of work. Recently, it's been adopted in algorithmic game theory, where people look at what the prediction can help if, because we have information limitations on agents' private information, if we have some predictions regarding these private information, can we do better? Ask the same type of question. And for this work, we focuses on how we use predictions in the settings of social choice. In particular, we're going to look at metric distortion with predictions. Okay, so let me just formally briefly go through the setup of metric distortion. So suppose that we're trying to find the next city to host EC. It's already done, but like let's suppose that we have a choice. All of us are somewhere on the planet. We're trying to find a city that minimizes some of the distance that everyone has to travel. But instead of trying to figure out where everyone lives and what's the distance to travel from every single one of them to all of the candidates, we're just going to ask people to tell us their ranking. So the voter one, and then of course, everyone would rank the place that are closer to them from the place that are further to them. So suppose that we get these preference profile that we call from this underlying metric. And then we're going to design a voting rule that only has access to the preference profile instead of the underlying metric. So the voter is going to be like, okay, voter one likes New York City more than Dubai, more than London, so on and so forth, and makes an aggregated decision about where to host the next EC. So suppose that the voter will choose New York City. This solution of the voting rule is then evaluated on the underlying metric instead of the preference, which is very important here. And then for this particular objective function that we're looking at, the solution, the quality of the solution is the sum of the distance from New York City to everyone. So let me just make the setting more clear and our objective more clear. We're looking at metric where there's N of voters and M candidates. And we're going to just denote the metric with the distance D because it fully describes everything. The only assumption we have for metric is triangle inequality, no other assumptions. This metric induces a ranking preference profile sigma right here. Oh, how do you do this? No,
The top, I think.
the top. It's okay. So this is the preference profile, just a bunch of rankings. We say that the underlying metric aligns with this preference profile if a voter indeed rank whoever is closer to him before. That's the definition. And then the key kind of like information limitation that the algorithm has is the algorithm does not have access to the underlying metric. It only has access to the preference profile, and it needs to output a candidate. But the social choice of the candidate is evaluated on some underlying metric. So if the social choice of candidate A is just the sum of the distance from candidate A to all of the voters. Okay, so we're going to define distortion as follows. We're going to look at the ratio between the candidate outputted by your algorithm, only giving access only to the preference profile, over the optimal candidate social cost of the same underlying metric that you're evaluated on. Notice that in here, we're taking the worst case of the preference profile, which is the input to your algorithm, and the worst case of all of the underlying metric that is aligned with your preference profile. So this is a very, very worst case flavor type of bound. In the first paper that introduced this notion of metric distortion, they also showed that no deterministic algorithm can achieve a distortion better than 3. This example is very cute and very small, but I don't have time, so I didn't include it. But if you're interested, we can talk offline. Okay, so that's basically the setup, and we know that we cannot do better at 3. So what is known to this problem? If you attended High on Beyond EC, this slide is probably familiar with you, but people have been working on this, long story short, and over a series of work, the first distortion 3 was proved by Gkatzelis et al. And Daniel Halper, who's right here. And afterwards, people are trying to come up with more simple voting rules that does the same 3 distortion bound. So in the worst case sense, the problem is solved. 3 is the best we can hope for, and 3 is indeed what you get. Let's look at it with the lens of predictions. So the question we wanted to answer in this paper is, can we go beyond 3 with the help of predictions? Specifically, this is very wordy. Specifically, what we ask if suppose we're given an untrusted prediction, C hat of the actual optimal candidate C star. So my prediction is the optimal candidate's ID. So like this guy is the optimal candidate. Can we design an algorithm that takes in both the preference profile and the predicted candidate that achieves a distortion better than 3 given a correct prediction and maintain an approximately optimal distortion even when the prediction is incorrect, right? Consistency, robustness. So let's just let me remind you guys what is consistency and robustness in this specific context. For consistency, we're looking at the worst case distortion given a correct prediction. So in here, the only difference between the big chunk of math that we saw earlier and this is that when you look at the maximum or the supremum taking over all of the underlying metric D, the metric has to be aligned with not only just the preference profile, but also the predicted candidate, right? Because that's that's what it means by me having a correct candidate. Whereas for robustness, it's just the classic worst case distortion overall. I'm gonna look at the worst possible preference profile, look at the worst possible metric underline, and whatever your prediction is, I don't care. Like you could be right, it could be wrong. I'm just gonna look at the worst case. And in terms of our result, instead of giving you the number, this is what we got. We get, this line is both positively and negatively, so it's a tight line. We achieve every single point on this line. This, I should first say that this is a robustness and consistency trade-off graph. So we propose a family of algorithms that achieve every single point on the line, and we show that everything. This is the best you can hope for. This is a Pareto frontier with respect to this prediction. In fact, we show something stronger in terms of a negative result. We show that this remains the Pareto frontier, even if the prediction is the entire metric instead of the maximum candidate. So I just want to spend a few minutes here of describing what's the difference between these two type of predictions. Notice that if your prediction is the entire metric, that means 2 things. First of all, there's more information for you to utilize in terms of your voting rules, right? It's like I know where exactly everyone is. I can do computations, do whatever, anything. The second point, which I think is more important, is that there are fewer instances to bind you in getting the consistency. Because what does consistency mean? Consistency means that I need you to give me some sort of guarantees when the prediction is correct. If your prediction is the entire metric, then there's only one instance that you're entirely correct. So I just need to perform well in that instance to claim a consistency bound. Whereas for our prediction, there's infinite amount of instances that might have one particular guy as the optimal solution. So for me to claim the bound that I did, I need to perform well in all of such instances. So so this kind of like is a very strong kind of a contrast in terms of the positive result and negative result we get. And I think the overall discussion about the type of predictions is a very interesting topic that I'm happy to chat more offline. But yeah, so this is a point that I really like. Okay, so for the rest of my time, I'm gonna try to just touch upon how we get this result. This result is actually based on the result that is without predictions, and we just simply applied it, and I think it's a cute idea. But for me to do that, please bear with me for another definition that might be a bit dense, but we can go through them together. Okay, so we're gonna look at something called a domination graph of a candidate. So domination graph is owned by some candidate. We need to always associate a domination graph with a candidate. So it's a vertex weighted bipartite graph. So you have voters on one side, each of them has a unit weight of 1. So it doesn't matter too much here, I guess. And then you have candidates on the other side, each of them has a weight of their plurality score. So whoever you know, plurality score is how many people rank the candidate first. So for candidate A, 2 of them rank him first. So the plurality score of A is 2. Voter 4 rank B first, so B has a 1. C also has a 1 by 2, right? So so far so good. Okay, what are the edges in the graph? The edges, some voter to candidate edge exist if voters prefer the owner of the domination graph more than the candidate it's pointing to. So weakly pointing to, weakly prefer. So for voter A, for voter 1, because voter 1 likes the candidate A the most, that means that voter 1 would have an edge to every single one of the other candidate because he likes A the most. So he prefers A over all of the other, weakly prefers A over all of the other candidates. For voter 2 likes A the second. So she only has an edge to A, she only has an edge to A and B instead of C. Similarly, for 3, it will be the same story as A. So she'll have all of the edges. And then for last one, it's only edges to AC thing. So that's the graph. Okay, the question is, we didn't come up with the graph, just for the record. The question is, why are we looking at this graph? Like we're doing distortions and now I'm doing this complicated graph constructions by candidate. What does it mean? Well, the density of the graph somehow says something about the popularity of a candidate, in which case we can translate it into a distortion. So just to make my point more clear, let's take it to the extreme. Suppose that this graph were to be complete. If every single edge exists, what does that mean? That would mean that the candidate who's the owner of the domination graph is ranked first by every single one of the candidates, right? In which case, of course, you should output that if you wanted to minimize distortion. If everyone agrees who's the best option, you should go with that option. So somehow there's a connection between the density of the graph and the distortion. But what's the right translation? How do we extract the right information from the domination graph to get what we want? We're going to look at what is called the perfect matching. So perfect matching here means something slightly different. It's basically equality of the weights. If you look at any one from the right and look at all of the people who are on the left that is matched with this guy, the weights should be the same. So for example, A is matched with 2 guys on the right, left. B is only matched with 1 guy on the left. That's it. So you just want to equalize the weight. And what does that give you? Suppose that in this case, my candidate A's domination graph has a match. Well, very nicely, if you have a fractional perfect matching in your domination graph, your distortion is at most 3. For whoever is at the beyond EC highlight yesterday, the proof that was showed is exactly the sort of the proof here. And then all of the distortion 3 algorithms, essentially the proof for distortion 3 utilizes this theorem, but they all have different types of ways of finding such candidate who has a fractional perfect matching. And the question I guess left here, there's 2 things that I wanted to point out about this theorem. First of all, this theorem doesn't say anything about the existence of such candidate. It just says, if such candidate exists, they're great. But I don't know if there's always this candidate. Second is, this result heavily relies on the weights that are set up. So I just built it in, right? Voters have unit weight, candidates have plurality weight. And then because if that's the way it's set up, then you get this fractional matching implies a distortion of 3. So Gkatzelis, Halpern, and Shah et al. In their first paper that got the 3 distortion bound proved this very nice result. So to show the existence of such candidate. In fact, they showed something even more general. So as long as if I were to look at any domination graph where the edge logic is the same, as long as the weights on the left are the same as the weights on the right, the sum of P equals the sum of Q, where P is the weights of the voter and Q is the weights of the candidate, then there always exists a candidate whose PQ domination graph admits a fractional perfect matching. Okay, great. We get more, like there's more candidate that exist who has a fractional perfect matching. Let's look at the same example with domination graph of candidate B. So it's the owner of the domination graph changed. Similar logic, I'm gonna have all of the edges. The weights change, so the voter 4 now has a weight of 2 and the candidate B has a weight of 2. There's a perfect matching, okay. Okay, now I'm here, what do I do? What does it mean that I have a perfect matching for this candidate? The question is, we don't really know anything about the distortion guarantees when the weights are out perturbed from uniform and pluralities to something else. So on the step of proving what we prove for with prediction, we showed the following result. It's a general upper bound for arbitrary PQ. So we showed that for any candidate who has a PQ domination graph, for any general PQ, instead of just those 2, you get this number. I know this looks messy, and then what does it mean? And I don't have time, so let's take it offline. But I think this, in a very high level sense, this is trying to capture how far away is your PQ graph from in terms of weights, the distance from the initial graph. Okay, and then this seems very arbitrary, like how is this connected with word prediction? Well, Oh, okay, sorry. The connection is very easy. So instead of telling you an algorithm that achieves anything, any point on my parallel frontier, I'm just gonna give you a weight. Because if I give you a weight, that directly implies a robustness bound by plugging into any PQ algorithms which already exist. So I just define a weight as a function of my prediction. Essentially, I just helped the predicted agent by a little bit. I keep everyone else the same as the initial vanilla PQ domination graph, and I added a little bit to the guy who is predicted. And then because of the results last year at EC, we know that there exists a bunch of algorithms that can give you some candidates in the PQ domination graph. PQ veto core, which is one that has a fractional perfect matching. So applying theorem 1, we directly get the robustness, and by utilizing the fact that predicted candidate is optimal, we can get the consistency bound because that's when it holds. In addition, we also get the smooth degradation that we wanted to for any choice of delta, basically for any choice of the point, where the delta equals to 0 corresponds to the consistency guarantee. And then as you can see, for different algorithms, it degrades at a different speed up until the robustness point that they're corresponding to and flattens out. So some of the interesting, I'm going to skip this. The two interesting open questions here that I really wanted to answer is that, first of all, it will be really cool to have a tight bound for general PQ veto core, and what does that mean, and all the implication that comes after that. And second is, we would just really like to kind of like promote this line of work in the lens of social choice or votings through this Learning-Augmented framework. And then I'm really happy to chat more about the predictions or the framework or that proof or what does that number mean offline. And that's it. Thank you.